Hello, everyone. Thanks for joining this new session dedicated to optimization topic in the area of hot rolling process. The presenter for this session is Mr. Corentin Pendaven, R&D engineer from ABS Centre Métallurgique company. So before we jump into the topic, let me briefly introduce Corentin and say a few words about his background. Corentin is a research engineer in simulation and processes at AB Centre Métallurgique in Metz, in France. This company, ACM, shortly, is the research center of Acieri Bertoli Safau, ABS, the steelmaking division of Danieli Group, located in Udine, in Italy. He graduated from ISAE Supmeca with a master's degree in mechanical engineering in 2015. He received a PhD in manufacturing process and mechanical engineering from Arts et Métiers Institute of Technology in 2021. His research work performed at the LCFC laboratory in Metz, in collaboration with ACM, was focusing on the numerical modeling and on the experimental analysis of shrinkage pore closure during the hot rolling of bars. Since joining ACM in January 2021, Corentin is working with ABS on the continuous improvement of their rolling and casting processes using material characterization, metallurgical expertise performed by ACM teams, and numerical modeling. The presentation for today is titled Thermal Exchange and Friction Coefficients Optimization of the numerical modeling of hot rolling. This said, I then hand over to you, Corentin. The floor is yours.
Thank you for the introduction. So my presentation is about the optimization of the simulation coefficient of a hot rolling process. So let's start with a small introduction. So as said before, ABS Centre Métallurgique is the research center of ABS, member of the Danieli Group, which produce and design equipment and plan for the metal industry. So our mission as a research center is the improvement of ABS processes using simulation, the development of new products, so for instance, steel grade with reduced sensibility to hydrogen embrittlement, and also to provide technical support with ABS customers, for example, to design their heat treatment, and also for external technical services such as mechanical testing. So to improve the team of ABS processes, we develop at ACM multiple simulation model of the process of the Udine production site. For instance, we develop continuous casting simulation with the computation of the carbon segregation pattern after casting. We also perform CFD simulation of the reheating it in working beam furnace to improve their energy consumption. And we also perform rolling simulations, such as the simulation of grinding balls manufacture to avoid the defect after the rolling and help to design the process to avoid also internal defects. So today we will be focusing on the hot rolling process, which is a performing process aiming the reduction of initial of the section of bloom to produce bars suited for further manufacturing process, for example, for forging of crankshaft or other automotive parts. And during this process, we also experience an improvement of the material properties with the reduction of the shrinkage pores generated during casting, and also with the fracturation of the cluster of inclusions during the rolling, and we also experience the refinement of the structure of the material. So why we use a simulation model in our industry? We use them to prepare the rolling of specific grade and avoid the quality issues during this rolling, help the design of new rolling sequences by optimizing the different operating parameters in terms of to reduce the cost, to improve the cost efficiency and limit the different trials during these design phases. How we built our different models? So we perform a first phase of model calibration and validation by confronting them with a measurement performed during the production, and we identify numerous matter parameters to improve our simulation. And of course, we need a lot of computational power to perform our finite element or CFD model of our processes. Today, we will focus on this calibration part of the different numerical model construct throughout the production teams. So the case study of my presentation is the rolling process performed on the Rotoforgia mill of ABS. This mill is dedicated to the rolling of large product with a maximum section for round products with an initial state of one diameter of 850 millimeters maximum at the entry of this rolling plant. And the studied rolling sequences will be rolling performed using 8 rolling stands with an alternation of loading direction to reach a final cross-section, square section of with dimension of 450 millimeters. Here you can see the evolution of the geometry of the bar during the studied work. So the different models used and parameters used to perform a simulation are first the material behavior. So we use compression tests to calibrate a phenomenological model, which is a Nansen-Spittel model with a range of identification in terms of temperature, strain, and strain rate that are representative of our forming processes. We will then have to define the different boundary conditions of the model, which are the different thermal exchanges with the heat transfer coefficient of convection, conduction, the emissivity for the radiation heat loss, the external air temperature and the die temperature, and also we have to define the friction parameter. For our simulation, we use a Coulomb limited choice curve model. So all those boundary conditions and parameters will be defined using an optimization procedure. So here we have a first set of parameters that I use to model the initial cooling performed during the descaling, where the oxide formed during the reheating phase are removed using water jets. So this part is a bit specific, so we have to use a different set of thermal parameters. And then we use thermal parameters or friction parameters that are representative of the condition that can be observed during modeling for the rest of the optimization. So to perform our simulation, we have to define 9 parameters using the optimization procedure. So the optimization procedure will consist of the improvement of the prediction of the rolling forces using the simulation model, and we compare the simulated forces with the experimental recorded forces. To do so, we construct an optimization procedure using P7. We have first the design space exploration and the selection of the different parameters performed by P7, an automated pre-processing phase that will set these different parameters into Forge. Forge is used to perform the finite element simulation with different cooling and rolling phases and interpolation between two rolling phases. And then the result of all these phases are automatically post-treated using P7 to compute the cost function and output it into the optimization procedure to pursue the study. So to perform our optimization, we use a workflow construct using the design space exploration with a surrogate-based optimization technique with a population of 75 samples, and the objective is the minimization of the cost function. We then have a composite block, which is composed of a pre-processing phase and post-processing phase to compute the different results. So during the pre-processing phase, we have 2 different types of blocks. One type of block when we configure the file, the text file used in Forge to perform the calculation, the configuration file linked with cooling stages, and the configuring file used to configure the rolling steps. So During these two block of the workflow, we simply use the text block of P7 with an automated field recognition in text to modify the different parameters involved in the simulation, and we use template files of the configuration to modify the entry parameters into form. Then the computation are automatically run by P7. Once the simulation is performed, we then have the post-processing phase, where first we extract the data of experimentation and we classify them in terms of torque, surface temperature, and boiling force used for the optimization. And then for each computed value, we use the post-processing to compute the mean of each value computed by the model. And we have a specific approach for the temperature, where we have an automation of the post-processing software of Forge, GLView, to compute the surface temperature and calculate the mean as to monitor the temperature during the optimization phase. So we focus here on the extraction of simulated force that will be used to compute the cost function used in the optimization procedure. So here is the example of the treatment of the force after the calculation. So we use text file to retrieve the different field computed in whirling whirl in Forge that are generated in a text file. We use the Python script block to process them by extracting the correct force field, computing their mean, and then we compute the cost function that will be output to the optimization block to continue the optimization process. Concerning the surface temperature, we have automated the execution of the software used to post-process the result of Forge. We have first we extract all the nodes of the part after the whirling. We extract also the coordinate of a sensor that is located in the steady state area of the bloom, where we want to compute the surface temperature, and then all this information and implemented scripts that are executed in the post-processor of Forge to compute the temperature on the surface of the bloom, and then compute its mean and compare it to the measured mean during the whirling operations. So here is the result of the optimization procedure with the evolution of the cost function during the optimization phase. We can identify the 4 design exploration phase which use 50 samples, and then the real optimization phase where the cost function is actually reduced to an optimum that we can see here. As a result, we can also compute automatically the correlation diagram that shows the contribution of each parameter to the cost function. Using this diagram, we can identify like the strongest impact of the emissivity of the initial cooling on the force of on the simulated forces. We also see a global strong impact of the thermal parameters. So it shows us that it is necessary to model the initial cooling with high precision to improve our model and give us a way to improve the modeling of the whirling process that we do. In terms of simulation results, we can see here in green the simulated forces after the optimization procedure with an improvement obtained. Also, in terms of final temperature, during the process, the installation of the pyrometer online didn't allow correct measurement of the surface temperature of the bloom when their sections are too high or their lengths are too low. But after the force pass, we can compare the temperature with our model, and we see an improvement using our optimized value. So we see a clear improvement in comparison with all the old results of simulation obtained using trial and error technique, which is time consuming to to do the pre-processing and post-processing, and we also see, as I said before, the optimization of the final temperature. So here, as a conclusion, we can see that using P7, we improve the modeling of our rolling process with an automated procedure of calibration, which uses a wide population of entry parameters. And also it helps us to identify the most impacted physical phenomenon or stage of the process that we will have to better analyze to improve our model. We also built a P7 workflow, which uses a lot of templates to modify the configuration file or to extract the result of the forge computation. We use a lot of relative file paths in P7 workflow. And also we put a convention of naming our process stage in Forge to have a workflow that is suited for faster adaptation, to use it to identify also the simulation parameter of other rolling process or other rolling simulation that we perform at ACM. In terms of perspective, after this study, we can say that we can improve our model by modifying the hypothesis used for the initial cooling to have a better initial thermal gradient in our parts to improve the result. And we can also have a better reliability of our model to perform further exploitation of our model. For example, the analysis of thermomechanical field to evaluate damage criterion, to help the quality team of ABS, and also to analyze internal pore closure as we do at ACM. So that's the end of my presentation, and it will be pleased to answer your question.
So yeah, many thanks, Corentin, for this detailed presentation. It was very complete. Yes, so I will forward you now some questions from the Q&A panel.
Yes.
So, first one says, the cost function that you showed includes force terms only, but the results that you showed later of the force also include temperature.
Yeah.
Do you optimize for temperatures also?
No, we only optimize for force and use the temperature as a monitoring condition, because on this one we only use the prediction data for the temperature that are lacking of information to perform the optimization using them.
Okay, so it was for monitoring purposes only that you showed the.
Yeah.
Okay, correct. We have another one, says the post-processing sub-workflow looks quite complex. Could it be reused easily in other similar cases to avoid creating it from scratch?
Yes, as I said, we use a convention of naming, and we just have to change in also relative path, and we just have to change the simulation file introduced into the P7 directory of the case to perform other simulation. I already do that on a second type of without any problem. The complexity is here in the number of steps in the rolling process, but once you have a similar one, you just have to copy and paste the block that containing each phase to operate.
Okay. Yeah, so many thanks. I think, yeah, we are just on time because now we started at 40, now it's 59. So yeah, so now you will have time to gradually switch to the next session. I remind you that now this session will stop. You have to actively switch to the next session. So just as a reminder, the recording of this session will be available. And now, well, we have some seconds left. So since we are on time, even some seconds in advance, we will simply let this session finish so people can move to the next one. Yep, so many thanks to all. Many thanks, Corentin, and see you soon.
Thank you to that advance also for occasion to present my work.
Yeah, thanks for presenting it here. Okay, I'll stop now.